Appreciate everyone being here today, making time to take a look at Autodesk's newest offering. For those of us specifically using the factory design utilities, this is a big deal. So FlexSim coming on board with Autodesk, it's a big deal, and I hope you guys learn a lot about process simulation, discrete event modeling in the presentation today. My name's Rusty Belcher. I'm going to be going through the introduction to FlexSim and using it in what-if scenarios with you. Appreciate you guys being here today, and I really want to jump right into it. I have a really brief agenda. We're going to take just an introduction to FlexSim and where it fits in the overall idea of laying out a digital factory. We're going to look at process simulation and its role in manufacturing. And we'll take a look at generating what-if scenarios with FlexSim's experimenter module. So new technology is driving manufacturers to take a better look at their existing or new processes. And process simulation is leading the way in that initiative. All product manufacturers are embracing innovation and new technology in order to maintain or advance their current production cycles. But incorporating new technology and innovative manufacturing practices, that requires a solid plan and not a wild guess. The path to innovation must start with a thorough analysis of your current process. It's not enough to say the process is inefficient or some new tech will solve our problems. It is critical to properly outline and identify your bottlenecks or your over or underutilized equipment and practices. Once the process is properly defined, your organization can move beyond a reactionary-based decision-making process to a more predictive, data-based plan. In this session, we're going to demonstrate how the current factory design utilities may be enhanced with the FlexSim process simulation application. You're hearing this term a lot these days. If you haven't heard Industry 4.0, you just haven't been listening a lot. It refers to the fourth industrial revolution or major disruption in industrial or manufacturing processes. These revolutions occur when some invention or innovation becomes so prevalent that industry has no choice but to retool and embrace the change. Think about how steam and then electricity and then computers completely changed the landscape of manufacturing. Well, now we're facing a new computer age, an age of AI and connectivity, machine learning, big data, and advanced simulation. And just as before, manufacturers have no choice. They must embrace these technologies or be left behind. Here's another new term, or a term you're hearing a lot, digital twin. A digital twin, as products and systems become more complex and connected with the ability to produce and share data, the ability to forecast and predict performance becomes a crucial part of your design process. The creation of a digital twin provides modern designers the ability to test unlimited what-if scenarios and to calculate optimal settings in a fully simulated environment. This method of process analysis allows us to achieve a data-driven, predictive solution to our system issues. Instead of, I don't know how to say this politically correct, instead of a wildly assumptive guess, all right? I want to be kind of careful how I say that, but I think you guys know what I'm indicating. We don't want to guess at our solutions. We want data to provide a predictive analysis to our solutions. Here's another new term that some of you might be looking at, especially if you're looking at FlexSim, discrete event modeling. It's a simple and versatile method used to describe, analyze, and simulate a system. By simplifying a complex process to crucial occurrences, the effort to develop a simulation model is greatly reduced. Advanced methods of randomness, dependency, and distributions are used to more accurately reflect the real world state of any given system. Now, we use the word discrete, and you got to take a pause there, to check our grammar. So we're talking about discrete, D-I-S-C-R-E-T-E, where things are individual, separate, and distinct. And that's the way we want to handle our processes. The processes that we outline in our simulation are individual. They can all be addressed. There's a stack of properties for every step for our process, and we can interact with those. We're not talking about the other discrete, where we're careful or circumspect about the language we use in order to avoid hurting people's feelings, all right? We're talking about discrete, where our processes are individual, separate, and distinct. There's a lot of examples of process simulation. It's been utilized for years in many, many different systems. Have you ever been boarding an airplane and wondered why they do it the way they do? Or you ever gone through airport security? That's a lot of fun, right? But those processes have been modeled and simulated over and over to produce not the best outcome for us as individuals, but the best throughput for a system. The science behind discrete event modeling is tried and true. It's been around for quite a while, but now with modern computers, we can utilize this scientific method to analyze our manufacturing systems. So some of you may remember back a couple of years ago, Autodesk had a tool called process analysis that used to be a part of the factory utilities. It was a simple flowchart analysis of your processes. I say it was simple. It wasn't 3D or it wasn't even 2D. It was just a flowchart. But each task along the way you could address individually. But it was never, ever intended to be a discrete modeling simulation. It was actually very much a deterministic way to look at a process. The FlexSim tool we're going to look at today is far more advanced than this tool was. And just in case some of you don't know this, Autodesk discontinued that process analysis tool in way of this new FlexSim functionality. So I want to give you an introduction to FlexSim and let you see kind of what the tool is, what's possible with the tool. So I'm going to reach up and play this. FlexSim is an object-oriented 3D simulation software it allows you to model any type of sequential flow or factory operation. If you manufacture products, build assemblies, or have a warehouse or a supply chain, then FlexSim is the simulation product for you. FlexSim is used to eliminate waste in any production process. Waste being any action that doesn't add value to the customer. Waiting adds no value to the customer. And it's expensive to have excess waiting time for customers' products or machines. FlexSim is a 3D simulation environment, so you can start with an AutoCAD file of the facility and drag out the resources for a true-to-scale model layout. The software also features a script-free logic building environment called Process Flow to help you describe even the most complex processes. The combination of drag and drop 3D technology and innovative logic building allow you to model any system quickly and efficiently. Then you can bring your real world data into FlexSim directly from Excel or a database. You can use this data, the latest available data, to make accurate predictions about future productions of your system. That's just a quick look at what the tool will do. We'll take a look at the what if scenarios coming up a little bit later. Let's take a look at where FlexSim fits into the development of a digital factory. Specifically Autodesk's overall solution for a digital factory. For a greenfield scenario, you will encounter the need for process analysis and FlexSim pretty early in the design phase. You'll see it over here with the rest of the tools in the factory design utilities. Now, it's important to note that FlexSim is a standalone tool. It works alongside of the factory design utilities. It's not included with them. If you're doing a brownfield scenario, you might find yourself documenting or analyzing the process of an established legacy system. Well, in that case, you might utilize FlexSim over in the operation phase of a design. Either way, it's available. It's a standalone tool, and it's available really at any point in time along the development of a digital factory. Let's take a minute and look at the challenges that many of us are facing when we're analyzing our own processes. Many companies look to optimize their current factories or build new ones, but they face a certain level of chaos. They don't fully understand their current processes. Their information exists in protected silos, and the required data is often scattered amongst many divisions in the organization. Understanding our tasks and processes is not as simple as you might think. Does anyone remember like the Family Circus comic strip from the newspaper? I know I'm completely dating myself here, but my favorite was always, it always involved that convoluted way little Billy would accomplish a simple task or a journey. That reoccurring scene was depicted so many times in the life of that comic strip, and all of those scenes together are now known as Billy paths. When you really start to document your processes, I think you'll be surprised you might have a few Billy paths of your own. So what tools are we currently utilizing today to document our processes? Well, many manufacturers use basic tools like spreadsheets or flowcharts or key performance indicators or capacity calculations. But all of these tools fall well short of the capabilities required to accurately depict a real-world system. These tools do not account for variability in time or randomness in distributions. They don't account for system interactions or interdependencies between processes and resources. These tools don't provide enough information to confidently face the risk in the downtime required to embrace a major change in your process. They cannot give you enough data to support or determine the long-term impact or benefit a change would make to your current system. Here's a couple of new terms for me. Systems are usually broken down into two types. All right. The first type is deterministic. That's where the outcome is fully determined by the initial conditions that govern the rules. There's no randomness involved. For any given set of starting parameters, the system would always produce the same exact result. If your system is like that, you're really lucky, because all you really need is an Excel spreadsheet. You can load your data in there, develop your formulas, and because it's a deterministic system, you can easily calculate what a what-if scenario. If certain parameters change, it would automatically update. But most real-world systems are very rarely deterministic. They're mostly going to be stochastic. A stochastic system is a system that incorporates randomness or uncertainty into its behavior and the outcomes of the simulation. In these systems, the same initial conditions can lead to different results, as the outcomes are influenced by many problematic factors. It's really it's a formula-based process versus something the real world has to deal with, where randomness is a part of our daily lives. Now, you might think that you can just ignore those random values and just use the averages in your calculations, but that practice inevitably leads to significant cumulative inaccuracies. This is so well known that these inaccuracies are called the error of averages. And this is often the outcome when you're trying to solve a stochastic system by forcing it into a deterministic calculation. You remember the Autodesk product process analysis? That was a deterministic way to solve a problem. But so many people were trying to take their real world systems and put it into that, and they all came back with the same problem. Hey, the results of this tool do not line up with what I'm seeing on my factory floor. This is why that tool was discontinued. Process simulations must account for things like randomness, the probability of different types of distributions, the interdependencies between our processes and resources. The fact that time, there's no set exact time that a task can take. A task can take, you see this where my task is taking me normally 8 minutes, but sometimes it can take 10 minutes, or if I do it real quick, I can get it done in 7. Well, there's a time variable involved there that we need to account for. But there's other things like service downtime, your allocation of resources. You might have to express some logical what if scenario. If this, then do this. If this, then do something else. And because we're dealing with randomness and variability, we can't just run the simulation one time. We have to run it as many times as possible so that the trends will become apparent. So at this point, you got to ask yourself, why would I choose discrete event simulation? I think the answer is pretty clear. Discrete event simulation produces a model that accurately represents the real world behavior of the system. An accurate discrete event simulation accounts for the effects of variability, interdependency, and time. Well, it is that time of the year. All right, I'm like everybody else. I'm kind of glued to the television on Sunday. So I want to start looking at these what-if scenarios. I mentioned this term earlier, predictive analytics. I have an incredibly powerful computer. We all do. I should be able to use it logically to analyze any situation, especially a situation that involves a lot of money. So now this is kind of a flight of fancy, but it's something that I've dreamt about. And I'll tell you right now, FlexSim does not do this. However, logically speaking, I should be able to take a computer and maybe hook it up to the video game Madden where you're playing the football games. And I should be able to load as much information as I can into a database about all the players on each team. I should be able to load data about their coaches and coaching staffs, how the players are doing, what their physical makeup is, what their mental attitude is, how they're feeling, what their past performances have been. I should be able to take into account the stadium and the venue, the referee squad that's on that week, the network that's covering it, when they're covering the game. I might monitor social media, and I could bring all of this data together into one simulation. And then I could play the game digitally. Now, listen, I couldn't just playing the game one time would not take into account all the randomness that I have built into the simulation. I'd have to play the game thousands of times digitally on the computer, maybe up to 1 million times. But each time I play the game, a different result would happen. But if I play it so many times, eventually certain trends would appear in the results. And I could use those trends and the data that supports them to make a better financial decision. Now, I'm not telling you that this is possible, but I have to believe. You can go online, and if you want to do some homework, look up online, go and look up predictive analytics and sports gaming, and it's kind of scary. And you know who's doing it is the people who are taking all the bets. They're invested very heavily into that. Now, I need to move on from that flight of fancy. FlexSim, you're not going to use this tool to predict the outcome of a big game, but we can use this workflow to analyze our manufacturing processes. We can incorporate parameters into our simulation and experiment with numerous solutions to our issues. The results of these simulations can be plotted, showing how the change affects the overall system or throughput. And when we're done, we have the data that supports our predictive analysis. Imagine a sandbox simulation where you could test your process changes, like the number of employees or resources dedicated to a task, or the number of machines or processors you're using, the capacity of a buffer that you're utilizing. You could modify your task times. You could check your or redo your failure rate and see what would happen if you change that, or the arrivals of some of the materials into your system. Well, listen, I want to get into the software and let one of the experts show you this. So we're going to initiate the video here, and we're going to let one of the experts from FlexSim walk us through how he handles a what-if scenario.
Hello, it's Regan Blackett again to help you explore more features of FlexSim and discrete event simulation. As a customer tech trainer with the PDMS group, I'll be focusing this presentation on one of FlexSim's key functionalities, its capacity for conducting model experiments. This potent analytical tool will help your customers in uncovering crucial insights, thereby guiding them towards improved results in their systems. In previous demonstrations, you saw the essence of the business case for using simulation and FlexSim. Your customers have processes, whether it's how they make their products, fulfill their orders, or manage their supply chain, and in those processes, there is waste. The complex interactions and logical elements of those processes make that waste difficult to discover. Only a simulation can tell us the whole story. What we've seen so far, the workflow for making these discoveries has been very manual. You go into your object's properties, make changes to their settings, run the model, note the results in the dashboard, and then do it all again for any potential changes you want to make to the model. FlexSim automates this workflow of making what-if comparisons through its experimentation system. Experimenting allows you to identify key inputs and outputs to your model, define different combinations of values for those inputs, and lets FlexSim run many iterations of those different scenarios. Once all scenarios have been tried, you have access to reports that let you make side-by-side comparisons between them. There are three key elements that support this workflow: the parameters table to identify the inputs you want to experiment with, the performance measures table to track the KPIs for the experiment, and the experimenter control itself. Here's an example model where we can see this in action. It's fairly simple. Parts arrive in random batch sizes at random intervals of time with random potential product types. They're transported to a tester by an operator where they have a random test time. There's a 20% chance that parts will fail this test and need to be reworked. Good parts continue to a packing station to be packed and shipped to customers. The combination of parts packed together is always the same: 4 red parts, 2 green, 3 blue, and 5 yellow. Now let's say we've built this model with the purpose of figuring out how we can maximize the number of pallets that we produce in a day. And we want to study the effect of an additional operator versus an additional machine versus a lower failure rate. Which of these options will produce the most, if any, benefit, and by how much? Because there's variability in this system, a single run of the model isn't going to tell us much about what we can predict about its outcomes. A lot like how a single game doesn't tell us much about a player's performance in the future. In experimentation, we run a simulation model a relatively high number of times and gather output data from all those model runs to tell us how a model can be generally expected to behave. Let's have a look at the different touch points for the experimentation system. Firstly, here are the parameters with the size of our operator team, number of available testers, and our test failure rate established as inputs of interest. Next, on the performance measures table, we are tracking the number of pallets per hour as our output of interest. Next, let's open our experimenter control by going to the statistics menu. And here you'll see we have configured our experiment job with a 1-hour warm-up time, a 10-hour runtime or stop time, and we've also established 30 replications to be run for each scenario. Below that, in the scenarios table, we have configured the different scenarios that we want to define for our experiment. Notice here we have a baseline scenario with a team size of 1, a number of machines of 1, and a failure rate of 20%, indicating that this might represent the current state of the model as it exists today. Below that, we've added another scenario where we say that we're going to add a team member, but notice that I keep the variables the same for the number of machines and the failure rate. Here, I'm trying to isolate the effect of just adding a team member on the model without worrying about any other confounding variables. On our next row, we have add a machine as another one of our scenarios. And here we'll have a team size of 1, number of machines of 2, and a failure rate of 20. Our fourth scenario, we've said that we want to see what happens if we can reduce the failure rate, and I've set the failure rate to 5%. Now, if we come to the Run tab, we're ready to run this experiment. So as you can see here, we have all of our scenarios queued up and ready to run. And so when we hit run on this, the experimenting engine begins to go to work. Now, this is something that can take some time depending on the size and the complexity of your model and how many scenarios and how many replications you choose to run. And the rate at which we can complete an experiment is pretty dependent upon your computer specs. Now we can see that all of our scenarios have completed and we're ready to see our results. So if we come here to where it says View Results, we can see now how our different scenarios stack up against each other. Now here we can see that on our baseline scenario, we can expect an average of about 5.85 pallets per hour. Each dot in the scatter plot represents the output of one replication of the model. For example, if you mouse over one of these red dots, you'll be able to see that this is the number of pallets per hour that we got during replication 21. Compared to another dot, this was the output value we got from replication 26. So a difference of between 5.33 pallets per hour and 6.44 pallets per hour. And now we can compare this to the result of adding a team member, and we can see that we have about the same minimum range of about 5.22 pallets per hour, but a much higher maximum of 7.78 pallets per hour. Here, there's a lot more variability. The range of potential values is much greater, but the average is 6.56 pallets per hour. And that's a gain of almost a full pallet per hour, right about 0.7 pallets per hour if we can add a team member to this system. If we take a look at our results for adding a machine, we can see the results are pretty similar to adding a team member with an average of 6.48 pallets per hour. And then if we were to reduce failure, our average sits at about 6.45 pallets per hour. So it looks like whatever we choose to do with this system, we can expect some pretty decent gains, but at the cost of a little bit more variability compared to the much tighter range of values on the baseline. Now, this scatter plot is one way to view your results. You can also come to this menu and choose to see a frequency histogram. If you wanted to see your results distributed like a statistical distribution, what kinds of values of our outputs are more likely to occur than others. For example, here on the baseline scenario, we had 8 replications that fell within 5.78 pallets per hour and 5.99 pallets per hour. Another useful way to analyze your results is to look at the scenario comparison chart, where here we're doing a test for statistical significance between all of our different scenarios. So initially, it does the comparison based on the first scenario. And so compared to the baseline, each of our additional scenarios is statistically significant when compared to the baseline. But if we change the basis for the comparison using this menu, compared to reducing failure is not statistically significant different from adding a machine, but it is compared to adding a team member and the baseline. In addition to these reports, you can also see information gathered by the experimenter related to your dashboards. Here on the Dashboard Statistics tab, you can see that if you had any dashboards in the model at the time of the experiment run, data for each scenario in each replication for each of these charts is gathered here. For example, this WIP versus time chart is showing for the baseline scenario, and this was the result that we had on the chart for replication 1. You can also see here for replication 3, replication 10, and so on. And you can see this for any of the different charts that we may have had. And again, the reason why we're seeing so much difference in each of these charts from these different replications is because each replication represents a different set of results given one set of random inputs from all the randomness and variation that we built into the model. So even though the model runs with the same inputs, because of the randomness, the outputs that we get are a little bit different. And again, this is why we want to run many replications per scenario so that the variability caused by that randomness can be kind of evened out in the results that we get. Now that we've explored some results a little bit, it's pretty common to start asking yourself some other questions about how the model might behave. For example, since we know now that changing the values of any one of our parameters, any one of our inputs, has about a half pallet per hour increase in our output, maybe now we're wondering, is there a way to maximize this? If we were to potentially change maybe all of the inputs, could we really maximize our throughput? So what if we add another scenario here? And maybe we want to name this something like max out. And we want to see what happens if we could have 2 team members and 2 machines and a low failure rate. What could that do for our system? Well, now we can come back to the Run tab and we can see our new max out scenario is queued up and ready to be run alongside our other scenarios. But since the other scenarios are already completed, we don't have to rerun all of these. These scenarios are already recorded, their data is set, and now we just have to hit run and we will begin executing the replications related to our new scenario. So let's have a look at what that did for us. So if we come back to viewing our results, again, we'll open that same report window that we saw before, but now we have our new max out scenario added to the end of the columns. And kind of interesting here, notice that the max out scenario appears to fare no better than the other 3 scenarios. The average on max out, 6.6 pallets per hour, and again, compared to what we would probably consider our best scenarios so far, the adding a team member also about 6.6 pallets per hour. Are these results a surprise? What would you have predicted them to be? This happens quite a bit when analyzing a simulation, where the results it generates can be surprising, and that's actually a good thing. One of the most valuable things a model can do is challenge your customers' assumptions or expose bias about how they think about their processes. If a simulation can confirm what you already believe about a system, that's great. But how much more valuable is it if it can reveal something they didn't anticipate? It could even prevent them from making a costly mistake. We've built many models over the years at FlexSim that have done just that. But how can we understand why these are the results that we're getting? Let's explore our data a little bit by taking advantage of the dashboard system. Using a special chart template called the scenario chart, we can explore that dashboard data that was gathered during the experiment. If we consider our work in progress versus time chart, the baseline scenario indicates a trend of ever-increasing WIP. Clearly, there is more work than our current system can push through to our packing stations. The green line on this chart represents the add team member scenario, and you can see that the WIP drops considerably, indicating that we are able to increase supply to packing and thus assemble more pallets. Adding a machine has a similar effect and parallels adding a team member, but with clear gap in their results. Reducing failure appears to follow pretty closely to adding a machine. But now notice on the max out scenario, WIP is put pretty much to 0. This would indicate that there is a point of diminishing returns where moving more WIP to packing stops providing any significant benefit. Now, why could that be? Well, let's take a look at another dashboard that's monitoring the average content of the finished goods queues that are directly before packing. The longer the bar, the more on average we have components in those queues. Of particular interest on this chart would be the bars related to the blue products and the yellow products. Notice on the baseline scenario that the blue bar is much longer than the yellow bar. If we look at the other scenarios by scrolling through the dashboard chart, you can see that that trend tends to hold up. The bars associated with blue products tend to be much longer than the other bars, and the yellow product bar tends to be much lower than the others. With the current mix of products, it appears we probably have too much red product, about the right amount of green, way too much blue, and not enough yellow. This looks like a potential bottleneck, so how can we resolve it? If we go back to the experimenter, I have 4 additional parameters here that will let me try different weighting values that change how likely each of our products are to occur. Let's try reducing the red product a little, keep the green as is, bring the blue down, and bring the yellow up. And now we'll go back to the Run tab, and we will run this new scenario with a different mix of products. And what do we see? Well, it looks like by changing the mix of products, we're able to greatly increase our pallet production to 7.3 pallets per hour with no change in the resources. Just by a smarter allocation of our products, we're able to get a big increase compared to the baseline and even our other scenarios that increase our resources. Clearly, we made some assumptions at the beginning of this model that we assumed that additional resources at the testing area of our model would increase pallet production rate. And that was true to a point. But it looks like beyond that, there's an additional bottleneck where we were waiting on product to be actually assembled at our packing station. By changing the product mix, we increased our pallet production much, much more than just throwing more resources at the problem. As you can probably see, this is where having a model starts to be really a lot of fun. Exploring the data in this risk-free environment that the model provides can be really engrossing and where real improvements for our customers can begin to happen.
Thank y'all for watching that and looking at that. Regan is he's the instructor I've been using to get familiar with the tool. He's a really great guy from FlexSim, and I appreciate working alongside of him. Look, let's finish up this webinar by reviewing the benefits that process simulation can deliver. Process simulation it's going to give you a better or a truer understanding of your dynamic system. It's going to provide true predictive analytics. It allows you to discover system latency. You can resolve resource utilizations. You can uncover bottlenecks or deadlocks. Of course, we want you to maximize your productivity. Of course, we want you to increase your revenue. But it's also possible to minimize your defects or minimize the cost for the overall system. This virtual sandbox or your digital twin allows you to kind of peer into the future. One of the big benefits is the power to look into the future and to understand the impact that multiple key metrics play in your system. I have given this presentation several times with FlexSim and just discrete event modeling as a science. It is by far my favorite way to conclude a presentation. I'm a big Back to the Future geek, all right? So just like Doc Brown said, your future hasn't been written yet. No one's has. Your future is what you make of it. So, to paraphrase a little bit, with FlexSim, your chances of making it a good one are a little bit better. Actually, I think a lot better. So listen, we've covered a lot in our short time together. I'm sure many of you will want to dig a lot deeper into the possibilities available with FlexSim. If you want to have a more in-depth conversation about this application, please contact your Imagineit account representative. We'll be glad to help you out as you explore the functionality of this tool. If you've got questions about today's presentation, you certainly take note of the info@rand.com email address up on the screen, as well as the phone number if you're looking to get in contact with us. And of course, I want to take this moment to say thank you for making the time to sit with us as we go through the presentation today.